Do you know stability of a building should be checked against lateral loads? In this tutorial, you will learn stability analysis of a medium-sized steel buildings as per Eurocode 3. This is part 26 of lecture series on steel design. For other parts, please have a look at link down below. Hey friends, if you're new here, I am Dr. Qureshi, a senior lecturer at a London University. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life. This is the second tutorial of lateral stability of steel structures. In this tutorial, I will solve a problem related to lateral stability and I will work out alpha critical to see that if second order analysis is required or not. I will be using S-frame as well to work out deflections for this frame. Let us now first of all work out alpha critical to see if second order analysis is required or not. The most important part that I'm going to cover here is the stability analysis. It covers the alpha critical. So how do we work out this alpha critical? Now this is really very important. So you need to consider these second order effects. Now this is another building. Its width is 28, its length is 49, and its height is 12.5, and the width of the bracing is 3.5. We are assuming a wind load of 0.8 kilonewton per meter square. That's the peak load. The area of the short face will be equal to 28. Now, the reason we are working out area of the short face because these two bracings, they will resist wind load in this direction. That's the reason. You will not work out area of the long face. It will be wrong. They are not resisting loading in the long face. They are provided in the long face, but they are resisting wind loading in the short face. And this is very important to understand. If you understand this concept, then obviously everything becomes easier. So area of short face will be equal to 28 times height of the building, which is 12.5. The wind load on the building will be equal to this area times the wind load, which is 0.8. Now this comes out to be 308 kilonewton. For two braces, the wind per frame will be equal to half of this, so 154. And at ultimate limit state, you will multiply it with 1.5. So this will give you 231 per brace. Now, how do we distribute it? Again, using the same logic at roof, it will be half of the height multiplied by the wind load divided by the total height. And then second and third, using the same procedure as I discussed earlier, because this has been divided into two floors, so 1.5 plus 1.5. So that's why you have 3 here. At the first floor, it would be 60.1, and bottom, you will have 32.4. For stability analysis, assume floor load per level for roof is 5.9, for floor it is 13.4. So total area of the floor is 28 into 49. This will give you total area of the floor. Now each brace stabilizes half of the building. This is the total area of the floor, but half of the floor is taken care of by one brace and half by the other. So that's why if there were 4, then we'll be dividing by 4. So 6, 8, 7. Now roof vertical load is different. It's 5.9. So this is for the roof, which we have written over here. And you will see why do we need these forces. Equivalent horizontal force, 0.5% of this is 20 kilonewton, which we have written here. For floors, we have multiplied 13.4, and this is giving us 46 kilonewton. So at each level, it is 46 kilonewton. At the bottom, we don't have anything because we don't have floor. Now we add up the loads to the actual wind loads. Now this will give me total load. So wind plus equivalent horizontal load. And then we have to carry out the sway and drift analysis. So then we have to carry out the numerical analysis to find out these values. Now you can use any of the software to work out these loadings, but I have used S-frame to work out these, and I will show you the procedure. Simply you put it in S-frame or StatPro or any software, and then you put this loading and then you provide the section sizes, and then it will give you deflections. So my deflections are roughly about this. The procedure that I want you to understand is this one. We have to work out this alpha critical. So alpha critical is h, means horizontal load, times small h, which is the height, divided by v, means the vertical load at that point, deflections. Again, difference of two deflections, difference of two deflections, difference of two deflections. So in this diagram for roof level, so for no P delta effect, alpha CR must be greater than 10. Here, for the first one, it's greater than 10. For third floor level, h, the load
is 149. Load means that you have to add up this top load as well. So alpha critical will be 149 plus 300 is the story height divided by V. Now V, you have to add up all the loads that's coming from above as well at this level, multiplied by the delta, which is difference of these two deflection that you got from the linear analysis. 6.8. So this is certainly not okay. For no P delta effects, alpha critical should be greater than 10. And again, for second level, you can see alpha CR is equal to H into H over V into A, load from the top, adding it up, and then again multiplying with these factors. Again, this is not okay. And for the first level, certainly this is not okay as well. So when this is not okay, it means that you need to consider P delta effects, because for no P delta effects, alpha critical has to be greater than 10, which for this building is not. Since alpha critical is less than 10, horizontal loads should be increased by amplification factor, and the amplification factor is this one. So 1 over 1 minus 1 over alpha CR, so amplification factor is 1.19. Everything has to be increased by 20%. So if alpha CR is less than 3%, then second order analysis need to be done. Second order analysis means that you have to carry out nonlinear buckling analysis to find out the force. But in this case, it's not less than 3, which means that we will just increase the forces. So the forces which were here, we increase it by 20%. Now we will consider these forces for designing the structure. And then these are the resources which are used. I-structure, stability of buildings. This is really very important. These 3 books. Then again, these books as well.
Let us now use S-frame software to work out deflection for the frame. I'm going to solve this problem that is taken from Steel Construction Institute P365 guide. This is the frame that I want to analyze in software S-frame. These are the member sizes which are given in this guide. And the purpose of this analysis is to find out deflections of this frame. So let us get started with this software. I will start with 2 dimensions, and then I will call it stability of frames. And then units, I will take the default units, and tolerances, I will take all the parameters as default. And design codes, I'm not going to design it, so that's absolutely fine. And I'm going to start the model from scratch. Then I'll finish. First thing I want to do is to edit the grids, and I want to display 1 by 1 meter grid, 10 grids at 1 meter distance, both X and Y. If you click OK, then you'll be able to display this interface. And I want to zoom it to the extent. Then for that, zoom to grid extents. It will show you the entire grid. First thing is to define the geometry. So here I'm going to start with member definition tool, and 2 joints and 1 joint. I will say 1 joint because it would be easier to create model using 1 joint, because we have different member sizes. If I start from here, in positive Y direction, I want to create this element, which is the column 3.5 meters. So I will go ahead and say plus Y, links 1, and then member length is 3.5 meters. So if I start from here, 3.5 member has been created. Then I would like to create 1, 2, 3 more members, and the length is 3 meters. So start from here, 1, 2, and 3. Then I would like to create a horizontal member, which is here in horizontal direction, 3.5 meters to 3.5, but now I will change it to plus X. So in that way, it will draw a member towards the right. And then I want to come in downward direction. So I will say negative Y, and distance is 3 meters, 3 meters, another 3 meters, and another 3 meters. Finally, I have minus 3.5 downwards. Click on here. Then you can click on 2 joints. Now I will join these members. I'll click this joint and click this joint. That will create beams for me. And then again, I will click this. And then I will create a bracing by clicking joints here and second joint, and again from here to here. In that way, I have defined the geometry. You can see it's this geometry. The next thing for me is to define the member sizes. So I have 2 materials, S275 and S355. Our first objective is to define the materials, but because we are carrying out linear analysis to find out deflections, this will actually not affect the analysis result, but I will show you how to define the materials in any way. Click on materials, right click,
And then Eurocode 3 here, I'm changing Eurocode 3 name as S275 first. And then here yield, I will say S275. And then I will add this material. So you can see this S275. I will add another material S355. And all I have to do is to add this yield stress and then add that material and click close. Now you can see that I have these two materials. Let me change the colors as well. So S275, let me change it to blue color, and S355, let me change it to green color. Let me say that all materials are S275, then only material which has S355 is this bracing. So all materials, this material 15 has been assigned, but for bracing, I will simply click on S355 and then click on here. You can see that its color is changing. It means that material has been changed as well. So once material has been defined, then my next step is to define the section. So section properties tool. So in section properties, I need to define the sections, and I have a couple of sections here. The first is 305, 127, 37. That is for roof beams. 305, 127. I will go to steel database and I will search here 305, 127, 37 UKB, and then simply I will click OK, and then I will add another material, and here simply I will go to steel again, 406, 178, 60, 406, 178, 60. Update. I've got this another section. Go to steel again, 203, 203, and 60. So I will update that, 203, 203, and 46. In that way, I have created these 4 sections, and then I will add another section, and here I will change this section to 168.3 into 6.3 CHS and click on these tubular sections, 168.3 into 6.3 CHS, and then update, and then OK. In that way, you will define all the materials, and you can see that all materials appear over here. But I will change the color of these materials. So first is green, and then UKB. Another one is, say, yellow. So now I have different members. So these members have to be assigned roof beams, 305, 127, 37. 305, 127, 37. So I will click on this one. It will assign this roof beam. You can see color has changed. And for floor beams, 406, 178. So floor beams is this one. So I will click on this. S1 has been already assigned. Second floor to roof columns, 203, 203, 46. So this is first floor, this is second floor. So second floor to column would be 203, 203 by 46. So I'll click on this, click on this one, click on this one, and then click on this one. Ground floor to second floor columns are 203, 203, 60. 203, 203 into 60, the color will change to blue. And then finally, I have to assign bracing section, which is 168.3 to 6.3. So click on that, it will change the bracing color. In geometry, I need to assign the supports as well. So we have pin supports. Pin supports means that TX and TY, so it cannot move in horizontal and vertical direction. So we have 2 pins here. And another thing I would like to do here, because when you create a model like this, it will assume that all joints are fixed. So I'm going to release the member release tool. I'm going to release all the moments. So clicking on the entire bit, it has released all moments. Now it will consider it as a pin joint frame. Once I have this, then I'm ready to apply loads. What loads are applied over here? Let us see. Loads are 47.7 kilonewton, 104.4. So let's apply these loads and let's see what we get here. Let me go to loads, and then I will click on joint loads. So here I will apply X force and -1. So the negative 47.7, 101.4. And I will click at these 2 points, and at bottom point I have 106.1 minus 106.1. If you click on here, you'll be able to see this loading. Now I'm ready to analyze it. So analyze, linear analysis. I need to save the files, a clean solution, no errors. And then I will go to graphical, and I would like to see the deflection tool. So you can see that it has deflected, but I would like to see the values, and click on options and diagrams, and here display values on diagram, and click OK. Now you can see I have 21.7 and 17.8, 12.5, and 7. The deflections are slightly different, but not much different from the book.